Okay, welcome to this video, guys. I'll be starting a section on mechanical vibrations, and hopefully this will be covering most of mechanical vibrations, single degree and multi degrees of freedom, forcing functions, damping, undamping, and hopefully I will make quite an extensive number of videos covering all these topics. And hopefully it's useful to you guys. Okay, so basically we need to first understand the background and basics to mechanical vibrations, and a system consists usually of three main components. Okay, so the first component that we often come along is a spring. Okay, so what are springs used for? They are used for storing potential energy. Okay, and I'm sure we've come across the symbol for springs. Okay, so they usually look something like that, or you can have weird springs like that, but for me I just draw them like that because that is just easier. Okay, so that will be my symbol for springs. Then we also come over any mechanical system will have a mass. Okay, and what does a mass do? A mass stores kinetic energy. Okay, and mass will in most cases on a free body diagram just be a box or a disk or whatever it actually represents, maybe a point mass. Okay, but mass is quite easy to identify. And lastly, this might be quite new to you guys, but a damper. Okay, so what is a damper? It is a way in which energy is lost. Okay, so it's important to remember that although we often make certain assumptions that there's no loss of energy, there is always a loss of energy within a system, and we have to take it into consideration in the real world. Okay, and the symbol for a damper looks something like that. And we'll be using these dampers, we'll be focused on viscous dampers. Okay, so once we've done that, we can just get a basic understanding for the degrees of freedom. Okay, so what are your degrees of freedom? Okay, so we can define degrees of freedom as the minimum number of independent coordinates required to determine completely the position of all the parts of the system at any time. Okay, so that might sound a bit weird, but let's just focus for now on a single degree of freedom. So let's say we have a wall right here and we've got a cart. Okay, so we can define, and let's say there's a spring right here. Okay, so we can define the position of this at this mass. We can define the position of this mass relative to the x-axis. Okay, because there's only translation here. No rotation is occurring, so we have a single degree of freedom. And we can also have that with a pendulum. So a pendulum, let's say something like that. It's being held up, and we have a coordinate system theta. Anywhere on this pendulum, let's say we had it here. Okay, then we can get the position using this angle. Let's say that's theta A. This would be this length, L cos theta A, and this distance here would be L sine theta A. Okay, so these are examples of single degrees of freedom. So yeah, okay, but we also can get double or 2 degrees or 3 degrees of freedom. So we need to take those into consideration as well. We won't be dealing with them right now, but an example of one would be the system right here. We've got one mass here and a second mass here, and they are separated by two springs, K1 and K2. Okay, these masses do not move the same distance each time. So this would be x1 and this would be x2. If, however, this was a rigid, let's say beam or something, then we could define this entire system using x1. But because we've got a spring right here, we need x1 and x2. Okay, but for now, like I said, we're going to be dealing with single degrees of freedom for quite a while, so we won't worry about that too much. Okay, So let's now think about what else we need to do, some basic things that we need to understand. Okay, so a concept that we need to understand is the concept of static equilibrium. Okay, so static equilibrium. Okay, so let's get an example of static. Okay, static equilibrium is essentially just when the mass is balanced by the springs, or the displacement of the springs is balancing the mass. Okay, so let me give you an example. Okay, so let's say we have the system right here, a spring, and we've got a mass m1. Okay, so in order to connect this mass, so initially the spring, let's say, was here, but we had to connect it to this mass, we have to stretch it a certain distance. And when it's connected, it actually moves back a little bit. And the mass, therefore, the final position of the mass is somewhere here, let's say. Okay, so now what we can say is that we don't have to take into consideration the mass of this object in our free body diagrams, all of that, because it is in static equilibrium. For example, the way we know this is if we cut this spring right here, this mass will fall. And therefore we know that the displacement of the spring is balancing the weight of the mass. And so in our Newton's method, which we'll discuss a bit later, we don't have to take into consideration the mass. Okay, let me give you an example where that isn't the case. So if we have an inverted pendulum and we've got, let's say, a point mass right here, okay, and let's say we have, instead of a normal spring, we have a torsional spring, okay, so a torsional spring, KT, and we've got a mass. If I cut this spring, absolutely nothing will happen because all the weight is acting straight down onto this rod. And therefore, when we do Newton's method, or any other method, in fact, we have to take into consideration this mass. Okay, this might not really make a lot of sense right now, but what's important to understand is just to understand whether a mass is in static equilibrium or not. Okay, let's do another example. Let's say we have a beam of some sort. It's balanced at that point. Let's call that point A. We have a spring holding that up. And let's say we have a spring at the bottom here as well. And let's say we also have some point mass M, and we've also got the mass of the actual beam. Okay, so if these springs did not exist, then, so let's change this up a little bit. If these springs did not exist, then because of this mass pulling down that way, this beam would actually have some form of a tilt, correct? Right, because this mass is pushing it down, so it's going to come to equilibrium somewhere here, or even steeper somewhere there, or it could even be vertical. Okay, but because of the fact that we have this mass, or because of the fact that we have these springs, we can actually say that this system is in static equilibrium. Again, how do we test this? Is if we cut this spring, okay, now we can ignore the spring on this side. We really just have to cut one spring and see if the mass moves. So if we cut this spring right here, let's say we cut it right there, this system will definitely move. And therefore, it is in static equilibrium. Okay, and let's do one final example. Let's say we have a system that looks something like this. So it consists of an L shape. Let's say it's balanced right there. We've got a spring holding here. Okay, and we have, let's say, it connected directly to a wall above it. Okay, so the system has a mass m1 as well as another mass m2. And for simplicity, we're going to assume that these masses can actually move independent of one another. So for example, m2 can move without moving m1. So m2 can be here and m1 can stay where it is, or m1 can move somewhere like that or like that, and M2 will not be affected. Okay, so now we have to test our theory. If we ignore this section, because they move independently, let's completely ignore this section of the diagram and now cut the spring. What happens? The mass is acting straight down, there's no moment being created because there's no angle here, and so this mass is not in static equilibrium. So we have to take into account this mass. M1 must be taken into consideration. Okay, let's see if this is true for M2. So let's say we cut the spring. Okay, so we cut the spring once again. What's going to happen? You have to remember that M2 is also being held up by that spring, right? So what's going to happen is that's going to fall. M2 is going to fall. So M2 has been taken into consideration by the spring's deflection. So we don't have to worry about M2. M2 is in static equilibrium. Yeah, so that's basically understanding static equilibrium. It might seem a bit difficult to understand right now, but once we get into some questions, it actually becomes much easier. And once you've got lots of practice, it'll almost become second nature to you. Okay, so now let's just run through some of the different types of vibrational systems that exist. Okay, so translation. So we have translational systems. Okay, so what is translation? Okay, it's translation. Let's say we have a cart, it's going that way, and there is no rotation. See, we can say that there is no rotation. All it's doing is translating upon one direction. So it's moving in that, let's say, x direction. Okay, for these types of systems, the force is equal to, let's say there's a spring attached here, and a, okay, let's actually draw this a bit nicer. Okay, so we have a nice box. Let's say we have a spring attached and we have a damper attached to a wall. And we've got a mass and a coordinate system x. Okay, translational system. It's only translating, no rotations occurring here. Okay, so in this case, the force is equal to k times x of the spring. So the force of the spring is equal to k times x, and this is measured in newtons. Okay, then if we want to discuss the energy of the spring, okay, so the energy of the spring is equal to half k times x squared, and obviously that is in joules. Okay, the units of k, let's just get that as well. Units of k is in newtons per meter, because k times x is a distance. K is in newtons per meter times a meter gives us our newton that we're looking for, so that makes sense. Okay, then let's move on to the damping force. So we can say the force of the damper is equal to c times x dot, and just like k has got a spring constant, c is the damping constant, and c is in units of newton seconds per meter. That might be strange, but let's see. Obviously force is in newtons, so what happens is our units for x dot is meters per second, because x dot is the first derivative of the position, which is the velocity. So when we multiply these two, meters cancel, seconds cancel, and we're left with newtons, which is what we want. Okay, and finally we can discuss the energy of the damper, which is equal to, oh sorry, we cannot use energy methods for dampers, that's silly. Okay, and then the inertial force, so this is related to our acceleration, is equal to mx double dot, and that again is in newtons. Okay, so that's for translational systems. Now let us discuss rotational systems. Okay, so what is a rotational system? Again, we went over that one of the simple rotational system is a pendulum. Okay, but In this case, we don't have a spring, but let's think of another rotational system. Let's say we have a system that looks something like this. We have a spring and a damper somehow. Just believe me, I'm trying to come up with this. Okay, connected all to one piece, and this rotates about this point as well. We've got okay. So let's say we have a rotational system like that. So basically, our rotation is that angle there, theta, and this angle here, beta as well. Okay, so for rotational systems, we use moments, not forces. And so our spring moment or torque, let's say torque M is equal to kt theta in Newton meters. And what does that mean about our kt? The units for kt are going to be Newton meters per radian. Remember, we don't really care about radians when we're talking about units, because it's dimensionless essentially, and theta multiplying by theta, which is in radians, would give us our Newton meters as we need. Okay, if we talk about the energy of the spring, okay, we can say that that is equal to a half kt theta squared, and again that is in joules. Okay, if we're talking about a rotational damper, we can say that ct, or we can say that the moment created by the damper is equal to ct theta dot, and again in Newton meters, and ct has got units of Newton meters seconds per radian. Again, weird units, but why does that happen? Because theta dot is going to be radians per second, the first derivative. These cancel, giving us final units of Newton meters as we require. Newton meters. And finally, for the inertial force or inertial moment, M, we can say that that is equal to J theta double dot, again in Newton's meter. Okay, so what is J? We can also use I, our first moment of inertia, or our mass moment of inertia. Okay, so usually you are given the mass moments of inertia, but the basic mass moment of inertia, let's say for a long rod, is 1 over 12. So I is equal to 1 over 12 m times the length cubed plus, m r squared plus m d squared, and d is the distance from wherever it is pivoting from to its mass position. Okay, so that's the distance d, 1 over 12 mr squared plus md squared. Okay, and let's see, the units come out as kilograms meters squared. Yeah, which is the correct units. Okay, so just to summarize everything we've done in this video, because I think I'll be stopping here, and in the next video I will be going over free vibrations of a single degree of freedom, and we'll be doing some questions in that case. But yeah, so just to go over, the system usually consists of springs, a mass, and a damper. We have different degrees of freedom in vibrational systems, and a very important concept is the idea of the static equilibrium, which helps us when carrying out problems, especially, and also just understanding our different systems. We have translational systems and rotational systems. But yeah, that's basically the background. I hope this was useful. In the next video, we will be going over, I think, a few problems on free vibrations and single degrees of freedom. So thanks for watching, guys.